All right. We just did constant pressure calorimetry. This is our second. Oh, come on, dude. There we go. This is our second calorimetry video, and we're going to do constant volume. Okay. A lot of this is the same kind of idea, but the details are a little bit different. Okay. We are still, oh, excuse me, we're still going to measure the surroundings so that we can calculate the system. Okay. This is, however, going to give us a delta U. Okay. Uh, and remember, U is internal energy. So we're going to see the change in internal energy when we get with this guy. Okay. Let's look here. Okay. Constant volume calorimetry ideas. Typically, constant volume is done with a combustion reaction. Okay. And it's in a pure oxygen environment, and it's usually trapped right in this sealed thing. So the constant volume means your container is completely sealed, right? There's no way for matter to get out, right? Gases don't escape, they're all trapped inside. What this is doing is, remember, in constant pressure, we ignored the work. In constant volume, we mess up our slides. Okay, in constant volume, um, we will convert heat, backwards, convert our work into heat. Since we're going to measure delta T, that's measuring the temperature change for everything. So it's including the work in that. So measuring our delta T is going to lead us to a delta U. Okay, typically what we do is our delta T is going to directly get us to a Q for the calorimeter, and the Q for the calorimeter will lead us to a Q for the system, or Q reaction, and that will lead us to delta U. Remember, the internal energy is the sum of all the kinetic and potential energies as we're doing this. Okay, typically when we're doing constant volume, we're using Q equals heat capacity times delta T. Okay, the heat capacity is determined by experiment for the calorimeter. So if you're going to do a bomb calorimeter, you've got a control experiment that you do that runs the calorimeter. Okay, so for example, that's why I have this up here. This is benzoic acid. So benzoic acid has a known amount of heat that comes out. Okay, and so you calculate the heat capacity. And if we were to say, let me do this for us while we're thinking about it. If we were to say that 1.000 grams of benzoic acid, that's this guy, okay? We don't need to know the formula or the molar mass or anything, but 1 gram of benzoic acid gives off, releases 26.38 kilojoules of heat, okay? And we know that the temperature increased by 4.673 Celsius. Okay, so what we've said here, this is only if we have to calibrate a calorimeter, but what we're saying here is this value is what's given. Like we know from consistent other experiments that if we put 1.000 grams of benzoic acid in there, we're going to get out 26.38 kilojoules of heat. Okay. Our calorimeter then is measuring that that 26.38 kilojoules of heat as 4.673 degrees Celsius. So for this particular calorimeter, we can calculate the heat capacity as, right, the Q that we have. So this would be Q, and this is our delta T as Q over delta T, which is going to be 26.38 kilojoules over the heat that we figured, the temperature we changed, 4.673 Celsius. So for this particular calorimeter, the C is 5.645 kilojoules per Celsius. I'm sorry, I'm writing on the picture, but I forgot I was doing this example. Okay. So after you've done the calibration experiment, you can come in and do the actual calorimetry experiment with your unknown thing. Okay. We're not going to do the calorimetry. Well, we're not going to do the calibration step on this, but that's how that's done. So typically the heat capacity of the calorimeter will be given. Okay. And so we'll have to just look for that. All right. Here's our example though for the calorimetry problem. 1.010 grams of sucrose is combusted in a bomb calorimeter. The temperature of the calorimeter increases from 24.92 degrees to 28.33 degrees, and we want to figure out delta U of the reaction. Okay. What we're given over here is this is the molar mass of sucrose. Sucrose looks like this, just for reference. This is the same thing as table sugar. Right? All the sugar that if you like buy a bag of sugar, it's sucrose. That's what we're talking about. And here is the heat capacity for this particular calorimeter for this experiment. Okay. So given heat capacity, which means we're going to be using this equation when we do it. Okay. Low hanging fruit first. Let's get delta T out of the way. Delta T is final minus initial, which is 28.33 Celsius minus 24.92 Celsius, which is 3.41 Celsius. Okay. We don't have an M here. All we have is heat capacity. So we can go ahead and plug this dude in. Do that. So here our Q of the calorimeter is the heat capacity of the calorimeter, 4.90 kilojoules per Celsius times 3.41 Celsius is 16.709 kilojoules. Okay, this has three significant figures because both our data pieces have three significant figures. Okay, now remember, we don't want Q calorimeter, we want Q reaction. And Q reaction equals negative Q calorimeter. So this is negative 16.709 kilojoules. Okay. All the heat that we did is going out of the reaction, out of the system and into the surroundings. Okay. Out of the system and into the surroundings. So there's our Q of reaction. What we want is delta U, and delta U is going to be given in kilojoules per mole. Okay, so this kilojoules is for 1.010 grams of sucrose. So we want to get kilojoules per gram, or kilojoules per mole. Oh my gosh, I'm sorry, kilojoules per mole. So let's convert our grams into moles. 1.010 grams. And 1 mole of that, this is why we were given molar mass, 342.34 grams. This is 0.0029503 moles with 4 significant figures. Okay, now we have kilojoules and we have moles, so we can just come back here and say that our delta U, oh shit, sorry. I somehow ended my slides and I wasn't ready to do that. Let's go back. Here we go. Delta, this is why I like recording with Zoom and not PowerPoint, because when you record with PowerPoint, you're screwed if you mess that up. All right, anyway, where I'm at, delta U is kilojoules per mole. So our kilojoules, negatives, oh, I did it again. I gotta stop laying my hand on the tablet, I'm sorry. Negative, okay, now it's just being persnickety. Why are you doing this? I just got a new pen because my old pen died. Let me pause this while I figure out my life. Good Lord, I don't know what I was doing, but I think I have my pen working again. Delta U, negative 16.709 709 kilojoules. Divided by the moles, we have 0.0029503 moles. Okay, so this is negative 5663.5 kilojoules per mole. And for three significant figures, we can call this negative 5660 kilojoules per mole. That is three significant figures. That last 10 seconds was hard. Okay. If you need me for anything, let me know. That's a bomb calorimeter experiment. Remember, bomb calorimeter is constant volume. I didn't say that when I was here, did I? Bomb calorimeter, right? The guy in here, this sample thing is typically called the bomb. It's very well insulated. Okay. Anyway, if you need anything, let me know. Shoot me an email. Come talk to me in my office. I'm here. I'll catch you later. Bye.